Lecture 3. Implication. Conditional statements. Conditional statements are statements of the form if A, then B, where A and B represent some statement forms. Symbolically, this is represented by an arrow symbol, with P, arrow Q, read as P implies Q. P implies Q has the truth value true if and only if P has truth value false or Q has truth value true. P is known as the hypothesis of the conditional statement, while Q is known as the conclusion of the statement. In the form of a truth table, we have that when P and Q both have truth value true, P implies Q has the truth value true. When P is true and Q is false, then P implies Q has truth value false. And when P has truth value false, then the statement P implies Q has truth value true regardless of the truth value of Q.
One may wonder why an implication with a false hypothesis has a truth value of true. This is because from a false assumption, anything can be derived. For instance, from the false assumption that 1 equals 0, we may derive the true conclusion that 0 equals 0 by multiplying by 0 on both sides. Alternatively, we may derive the false conclusion that 4 equals 2 as shown in the example below. The importance of the implication connective comes from the fact that many theorems come in the form of conditional statements or biconditional statements.
In the natural language, A implies B can be said in a variety of ways. For instance, B if A then B, and A is sufficient for B. Some of these ways take a more contrapositive tone, such as A only if B. A only if B means if we do not have B, then we do not have A. That is, if not B, then not A. That is, a conditional statement of the form if not B, then not A. This is known as the contrapositive of the original statement form A implies B. The implication logical connective also gives rise to some useful logical equivalences, such as the implication law. That is, that P implies Q is logically equivalent to not P or Q. Below is a truth table proving the above logical equivalence. As we can see, for any assignment of truth values to P and Q, P implies Q and not P or Q have the same truth value, and thus they are logically equivalent. Now, the negation of P implies Q is logically equivalent to the statement form P and not Q. Below is a proof of this logical equivalence using inference laws. Converse, inverse, and contrapositive. Every conditional statement P implies Q has a converse, inverse, and contrapositive. The converse of P implies Q is the statement form Q implies P. That is, a swapping of the hypothesis and the conclusion. The inverse of P implies Q is that not P implies not Q. That is, we apply negation to both the hypothesis and the conclusion. And finally, the contrapositive of P implies Q is that not Q implies not P. That is, we both swap the conclusion and the hypothesis and then apply the negation. Let us have a look at an example of these. Let's define the statement variable P to mean I am in South Africa, and the statement variable Q to mean I am in Africa. Then P implies Q would stand for if I am in South Africa, then I am in Africa, which in fact has a truth value of true. The converse of this statement, Q implies P, would be if I am in Africa, then I am in South Africa. We'll notice from the picture that this is not necessarily true. For if one is in the DRC, one is in Africa, but not in South Africa. Thus, the converse has truth value false in our case. The inverse, not P, implies not Q, would be if I am not in South Africa, then I am not in Africa. This inverse too seems to have truth value false, because one could be not in South Africa and in Africa. The contrapositive, not Q implies not P, would be if I am not in Africa, then I am not in South Africa. We will notice that this has the truth value true, the exact same truth value as our original statement. In fact, the original statement is logically equivalent to its contrapositive, whilst the inverse is logically equivalent to the converse. This explains why both our contrapositive and original statement both had truth value true, and our inverse and converse both had truth value false in our previous example. As a final fact in this conditional statement, contrapositive, converse, inverse mix, we have that the inverse is in fact the contrapositive of the converse. Finally, we have a look at biconditional statements, that is, statements of the form A if and only if B, where the if and only if is often abbreviated by if with a double F. P if and only if Q has truth value true if and only if P and Q have the same truth value. That is, P if and only if Q is true only if both statement variables Q and P are true, and true only if both statement variables P and Q are false. As a fact, we have that P if and only if Q is logically equivalent to the statement form P implies Q and Q implies P.